Okay, so we didn't quite get finished up what I wanted to do last week. Partly because maybe I was a little optimistic, partly because Citrix was a little slow, and partly because some of you hadn't dealt with fuzzy membership functions before. So I wanted to follow up on that a little bit, and I'm going to talk some about it in class, but I wanted to provide you this narrated set of slides and hopefully video that you can go back and use as a resource later on when you're trying to figure out how to create fuzzy membership functions inside of geospatial models. So where to start? Well, we always begin with a DEM when we're doing this sort of stuff, or at least the sort of stuff that we were doing in class, which was we were looking for a particular location that met a range of criteria that were outlined to us, and they were all topographic criteria. In other words, we're looking for a certain elevation, a certain aspect, and a certain slope. So we started with a DEM, and the one we had, sure enough, did not have an attribute table, and so we had to do some massaging of our data to get it ready. And so we went to the data management tools, raster data toolset, copy raster, use the copy raster function to select the raster without the table, and you made a blank and made blank the no data value field, selected the pixel type to give us integers in the range we needed. So for some stuff you can do 8, but for most things it's going to be 16. When in doubt, choose assign in case you have negative numbers and they matter. And then last, we selected the format that we wanted it, which was an Esri grid. We made sure that we named it something we knew what it was and saved it where we could find it. Once you do that, the next step is making an attribute table, because to this point all those steps that I just talked about on that previous slide were really there to do one thing. They were there to create a raster data set that we could use to do this. Now we have to actually make the attribute table. Data management raster properties toolbox, build raster attribute table. Pretty simple, straightforward. Find the tool, select it, it's done. Check the little box that says overwrite, so it just adds it into the existing one. Really simple. Once we have that, we got to make the other layers that we need, not just the elevation, the slope, and aspect. And so in Spatial Analyst, under Surfaces, that's where the slope and the aspect tools are. You simply select one, in this example slope, select % degrees. It doesn't matter which one as long as you understand what those units mean and you know that you're picking the ones you want. And then just like that, run the tool, you have a slope layer. Same way with aspect. Find the tool, put in what you need, run it, now you have an aspect layer. The problem is those last two layers, again, no attributes. So let's fix the slope layer first, and then we'll fix the aspect the exact same way. Basically, you're going to go back and do the make attribute table the same as you did on slides 2 and 3. Okay, so now we're going to make a fuzzy, and this is basically just a sequence of selecting attributes and field calculations. Nothing more complicated than that. We're looking for an elevation range between 800 and 1100 meters. 950 is perfect. So we're going to open the attribute table, add a field, calculate the field as zeros. We're going to go select by attribute, make a new selection, select everything above 800. Then from that, select everything less than or equal to 950. Apply this equation and it all works out. So what does it look like? We start out with a table. Here's our data set. We add the field, long integer, call it fuzz. Then we use the field calculator, make everything 0. Next we select by attributes everything above or equal to 800. Then we select from that selection everything less than or equal to 950. We go back to field calculator, punch in that equation, and now you can see that those values now have numbers associated with them, not just zeros. And then we go right into it, select by attributes again. Now we're selecting everything that's above, or everything that's less than 1100, and then we apply the same set of equations. This time we have to do the inverse. And once we do that, so now we've got everything selected that we wanted that's outside of that range. We put this -1 in here that flips it all around, And that makes it now calculate out the downhill side of the equation. And you can now see that we're going from at 950 up to 1100, which is the sort of the next step up. We now have going from 100 going down as the numbers increase instead of the opposite. Alright, so how does all that work? Calculating using the 0 to 1 equation. Pretty straightforward. Clear your selected features, do all the stuff. This is the steps that I just covered. Greater than 950, up to 1100, and so on. And you can work through the equations and it'll all work. I want to point out something. Notice that I changed the minimum and maximum values. When you're working it with subsets of your data, your minimums and maximum change. It's not the minimum and maximum of the whole data set. It's the minimum and the maximum of the data that you're working on or what you have selected. Again, so use your 0 to 1 equation. When you put that -1 in there, basically it takes -1 and subtracts some fraction between 0 and 1 that the equation would give you from that. By subtracting it from 1, it basically just flips it, gives you the inverse, and then when you multiply it by 100, everything's back to normal. And that's how you create your fuzzy elevation functions. Now, the process we just did, you're going to repeat it for the slope and the aspect. Pretty simple. Aspect, south 180 is what we're looking for. South's perfect. East is the minimum, west is the minimum. So 90 and 270 are okay, but anything that's below 90 or above 270 is not. So we have to make those things in zeros. Slope, same kind of thing, except in this example we're looking for between 12 and say 24%. At 12, everything's great. At 24, it's not as much great. So before we had east was the minimum and all that, now we've got to think of it in terms of slope. So if 12 is better than 24, you need to tinker with the equation. The same equation that you used for the 90 and the 270 and stuff with east and west minimums, it's not going to work. Why? Because as the slope increases, the values will increase with the normal 0 to 1 equation. You want the inverse of that. You want the 12 to be your highest score to decline as it increases. So you need to use that inverse scale. So here's an example. We have all the data. If you just apply the normal 0 to 1 scale, you can see that as our value, our slope, goes from 12 up to 24, our values go from 0 to 100. If we put that negative in and do the inverse equation, it runs in the other direction, which is what we want. So now that you've got all that done, what's next? Well, it's not quite as simple as you think. When you add that field, you're sort of doing it at the peril of raster principles. Rasters, have one value for every cell, and that value is the one that you were calculating the fuzz number from, not the fuzz number. So you have to make a new raster. You have to make one that has the value that you just calculated. So we're going to do that using a tool called lookup, where you input the raster, you input the field that you want, which in our case would be fuzz, select the output for it, and then run the tool. Now, in this example, you can just punch it in and it'll give it a name. It'll put it in the same geodatabase that you've been working in, and whatever your default is, and it'll give you something that looks like this. This is the elevation one, and you can see the values where it's high, values that have the highest score. In other words, at around 950 feet, they have, or 950 meters, they're green. As you go above or below that, they get progressively lighter in color. So once you've repeated that step for your other two fuzzy layers, now you've got 3 layers like this that have scores between 0 and 100. The next step is to go in Spatial Analyst and go to the Map Algebra tool section and find your raster calculator. Now, our perfect location should have a score of 100 in each of our parameters, and so we're looking for something to have a value close to 300. And Raster Calculator simply stacks your rasters up, lines up all the grids, and then it does whatever math function you tell it from one grid to the next. In this example, we took the looked up elevation value, the looked up slope value, and the looked up aspect value, and we simply added them together. And so if it was a single cell that had the highest in each one, the value we would come up with would be 300. Now we'll see what happens. Once we run the tool, kaboom, it looks like it didn't do anything. Okay, in the end you get this, and this is our combined raster calculation from those three values, and you can see that the higher values are the lighter color, and the highest score we got was 297. The lower values are the darker colors. And so you could take something like this and identify the places that meet your criteria where you're searching. And there's a whole lot of other things you could do with it beyond this, but this just shows you how you can basically create fuzzy membership functions from raster datasets and combine them together in a really cool, really simple, really straightforward modeling approach. I hope this helps, and again, if you ever have questions, give me a call, send me an email. Stopping by on office hours is best. Coming in before class is even better. Staying after class is okay, as long as you don't mind getting home really late. But otherwise, yeah, I'll help you work these out. Figure out some really cool ways to do some really neat things.